Hello everybody. Welcome to the Statistical Physics Journal Club. Today we have with us Sourabh Lahiri from Birla Institute of Technology, Mesra. So he'll be talking about stochastic thermodynamics and its applications in the study of microscopic active heat engines. So Saurabh, you can start.
Okay, thank you, Anne, for the introduction. And I would like to thank the organizers of this journal club, and in particular, Ian, for inviting me here. This is a topic that is relatively new in the field of non-equilibrium statistical physics, and has attracted the attention of scientists over the past decade or so. There are some new terms which need explanation, like stochastic thermodynamics, microscopic heat engines, and microscopic active heat engines. So we will try to give a basic introduction to these systems as we go along. The work that I'll be discussing today have been done in collaboration with Aradhana Kumari, who is my student at the IIT Mishra, Dr. Priyashankar Pal, he was a postdoc at the University of Maryland, and Dr. Arnab Shaha, who is a faculty at University of Calcutta. This is the outline of the talk. There will be a pedagogical introduction to stochastic thermodynamics initially, and then I will move to stochastic heat engines. We will discuss the model that we have used and the analysis of the thermodynamics of this engine, finding efficiency, efficient power, and then we will give a simple application in which this engine is connected to a one-dimensional version of a flywheel. Okay, and then I will summarize and conclude the talk. If there is any suggestion or comment, please stop me, because I mean this is a relatively new topic and many new ideas can be incorporated. Okay, now how is the static thermodynamics of small systems different from the thermodynamics of large systems that we study in our graduate courses? We know there are three laws of thermodynamics. One is the first law, which says that energy is conserved. Okay, it says that the change in energy, which is delta E of a system, can be caused due to two reasons. One can be due to the work that is done on the system, or the other can be because it dissipates some heat into its surroundings. Next is the second law, and one of the most popular statement is the statement of non-decreasing change in entropy. So if I consider the system, it's in contact with its environment, and if I consider the total entropy of the system and the environment, then the change in entropy is non-decreasing with time. Okay, it may become a constant at equilibrium, or in general, it increases with time. And again, this is the most commonly used statement of the third law, which says entropy of a system reduces to zero when the temperature reaches absolute zero. Okay, but we know that these three laws are valid for thermodynamic systems, where the approximation is that the number of degrees of freedom are large enough, and we can consider the degrees of freedom to be infinite. Okay, but suppose this approximation breaks down, what happens in that case? Okay, and this typically happens when systems are of dimensions of nanometers. Okay, and in that case, this approximation doesn't hold. Okay, and I mean, such systems usually have the following property: the energy exchanges are of the order of the thermal fluctuations in these systems. And the typical energy exchanges are of the order of piconewton multiplied by nanometers. So if I apply a force of piconewton on the system, it moves by an order of nanometer. Such systems show some strange properties which doesn't seem to always abide by the laws of thermodynamics. Let us give an example where we consider an isolated box that contains a large number of particles. Okay. Now they're evenly distributed throughout this box, and roughly 50%, I mean, almost 50% of them are in each half of the box initially. Now, suppose at a later time, I want to find this configuration. So all the particles are congregated in one half of the box. Now, as you can guess, the probability of observing this kind of a process is very unlikely. So each particle has a probability of being of half of being in one half of the box. So the total probability of all particles congregating in one half is 1 by 2 to the power n. And if n is of the order of Avogadro numbers, then we can as well call it 0. But consider this system. There are two particles, each in one half of the box. And what is the probability at some later time that we find both the particles in a single half? Now, this is a quite likely process. Okay, in fact, 25% of the times, almost in 25% times, we'll find that if we start with this configuration, we end with this configuration. Okay. Now, can we say that the second law is violated? Because it seems that the entropy is decreasing in this case. Should we say second law is violated? No, because the quote-unquote correct statement of the second law is actually to that a while later. But this example should be enough to convince you that the thermodynamics at small scales is different from the thermodynamics at large scales. Okay. Okay. Now let us analyze this this behavior in more detail. Suppose we generate a histogram of thermodynamic quantities by performing an experiment repeatedly. Consider that an experiment with a macroscopic object, and we are measuring the entropy of this, and we are performing this experiment 10,000 times. So that builds an ensemble, and we are trying to build a histogram of the probability of the entropy generated in each of these experiments. Now, typically, what we will find for a large system is that every time we get the same value. Okay, no matter how many times we perform this experiment, every time we get a single value of total entropy. The fluctuations are negligible in this case. Okay, so we can approximate the distribution by a delta function. However, if we go to smaller systems of the order of nanometers, then the distribution looks much broader. Okay, so the mean of the total entropy, whatever is the value of this mean, is comparable to the width of this distribution, which is why it looks like a broader distribution. And a portion of this distribution can even enter the forbidden region, right? So in the shaded region, you see that entropy is actually decreasing, which is not allowed by the second law. Okay. Now, for this system, I can use the usual second law which we study, namely delta S total is larger than is non-negative. Okay. For this system, this is not the case. But if we apply this average, ensemble averaging, then it can be strictly shown that this quantity will be non-negative. Okay, the average of this distribution is somewhere around this peak. Okay, and what I'm saying is that it can be rigorously shown that this peak cannot lie to the left of this vertical line. So that shows the basic difference between the thermodynamics of these two systems. Okay, in fact, this is the more refined statement of second law, and ideally, this is the same law that should apply even in the macroscopic case. But because in macroscopic systems, the distribution doesn't have any weight, it's a delta function distribution, we don't care about this average. Okay, ideally, we should have put this average, but because it's delta function, we remove this average, and the law is equally valid.
Hi, can I ask one question?
Yes. Sure.
So in this distribution, like, is it known how does the MST of this distribution decay with number of degrees of freedom?
The distribution decays with number of sorry, I didn't
No,
get. I mean,
not the
by decay, what do you
distribution,
mean?
not
Yeah.
the not the distribution, but the uh, uh, mean square displacement over, yeah, variance of the uh, entropy. How does it decay with?
I mean, if
Sorry.
are asking about the variance in entropy, of course, it will decrease with the if you increase the number of degrees of freedom, because that is what is that is the result of central limit theorem. If the degrees of freedom become larger and larger, this width becomes smaller and smaller. And if it's become very large, if it becomes very large, then it will reach this limit.
Okay.
Right?
Okay. Thank you.
Oh, okay.
Saurabh,
Yes.
I have a question. So this
Yeah.
right picture is not really is not correspond does not don't really correspond to the two particle in a box problem that you have talked about, right?
Hmm.
Does it correspond to that?
Two particle in a box will have what minus. No, I think it has only two values. No, the probability distribution is discrete there, so this doesn't correspond to that.
No, in the two particle in a box means you are talking about two particle in isolated box. Particles are not
Yeah,
getting energy from the walls, right?
yeah.
So in that case, yeah, what is this entropy? You can
No,
define.
the variable is this. The states are discrete, right? So it is either the left half or the right half. So that is what I mean by two particle. And we don't have the continuous distribution. If the particles are on two sides, then the entropy, if you calculated by the Gibbs distribution, it will be minus half log half minus half log half. So um, that will give minus log 2, right? Right, and the other case, if both the particles are on the same half, that will be log of 1 by 4. Right? Does that sound reasonable?
Okay, but you are considering
Yeah.
initial conditions from some uniform distributions like that.
Initial is uniform, so that's what I wanted to show, that in a large system, if I start from uniform distribution, it remains uniform. But for a small system, I can observe deviations. Namely, it can become non-uniform.
Okay, continue.
Okay. The mathematical definitions were given by Sekimoto in the late 90s, and he gave prescriptions of how to define thermodynamic variables in for continuous variables. Okay, he started with the Langevin equation. Now, this is the equation that describes the motion of a Brownian particle in a medium. Okay, on the left-hand side, we have the mass into acceleration term. On the right-hand side, you have a damping term because the particle is moving through a swarm of particles of the reservoir. And if we have a conservative force, then we have the gradient of potential as well. Up to these two terms is simply the Newton's equation with damping. Okay, and the evolution is deterministic. But now, because there are thermal fluctuations, this Brownian particle is receiving random kicks from the surrounding molecules. There is a random portion of the force. This is a random force, and it's usually assumed that this is delta correlated in time, which turns out to be a reasonable assumption in most cases. Okay, and what Sekimoto did was he saw that this is a force balance equation. We have forces on both sides, and he multiplied both sides by the displacement in some short time dt. He multiplied both sides by dx. Now, force, if it is multiplied by dx, it will give dimensions of energy. Okay, so force balance equation has got converted to an energy balance equation. Okay, now I mean, one can guess that this will somehow be related to the first law, because the first law is also an energy balance equation. So let us see how that comes about. So you multiply both sides by dx and then rearrange the terms. The terms can be rearranged in this way. Okay. On the left hand side, we have minus gamma v plus xi t. And these are the forces generated by the collision of the Brownian particle with the surrounding molecules. Okay, so this is the force on the particle by the surroundings, and if there is an additional minus sign, as it is here, this must be the reaction force of the particle on its surroundings. Okay, so let me repeat this point. These two forces are the forces that are applied by the surroundings on the Brownian particle, and because of this additional minus sign, this is the reaction force of this Brownian particle on its surroundings. Okay, now reaction force multiplied by dx, this is the work done by reaction force. And what else can that be other than the heat dissipated? Okay, and that is how this is interpreted. So this portion is the heat dissipated in a small time dt. Okay.
Sorry, would you please repeat why you interpreted how you interpreted the term on the left hand side?
These are the forces due to the bath on the particle. The particle is moving in some reservoir, so the force acting on the particle, and this minus sign. So if you add a minus sign, this must be the force in the opposite direction. So this is the reaction force of the particle on the bath, right?
Okay. Okay.
And reaction and the work done by this reaction force on the bath is lost into the degrees of freedom of the bath, and that is interpreted as the heat dissipated. Okay.
Okay.
Now on the right hand side, this is easy to see. This should be the change in internal energy, because this is a summation of kinetic and potential energies. Okay. Then compare with the first law. This is the heat dissipated. This is the change in internal energy, and the third term must be the work done on the system. Okay, and that is how he defined the work done dW to be the last term on the right hand side. All right. Well, all these are for a very short time dt, right? This dx is a displacement in a very short time dt. Now, if we want the thermodynamic quantities over a period of observation tau, what do? We integrate over time, of course. So if we integrate, then these are the expressions for work, change in energy, and heat dissipated. These are the definitions that we will use in analyzing or studying the thermodynamics of our engine. Well, this must be, let me get into stochastic engines. And first of all, let me say this is the cover page of a book that must be familiar to many of you. This is the Fantastic Voyage Destination Brain by Isaac Asimov. And the book is a story about a group of scientists who have been miniaturized and injected into the bloodstream of another scientist who is in coma. Okay, and this group is supposed to reach the brain of the scientist and this unconscious scientist and collect some information from his brain. Okay, now although the miniaturization of human beings is far-fetched as of now, people conceive of tiny robots can do similar jobs. Okay, so these kinds of robots can find a lot of applications in medicine and healthcare. Like they can go through the bloodstream and repair some damaged tissue somewhere, or they can remove a clot somewhere. Okay, so even they might be employed to fight against cancer cells. Okay, now one of the hurdles in devising these machines is what kind of engines will power them. We need to find commensurate engines, because we definitely cannot connect them to large engines, because they cannot endure that much of power output of the large engines. So the engine should also be small, so that the power output can be endured by these engines, these microscopic machines. Okay, and that is why such systems are intensively studied nowadays. Okay, a Brownian Carnot engine was proposed theoretically in 2008 by Schmidl and Seifert, and has also been realized experimentally, okay, in this paper. But we will talk about a slightly different model, which is not a Carnot engine but a Stirling engine. Okay, this was used by Blickle and Bechinger in his experiment in 2012, and the same model was used by Ajay So's group later to study active engines. Okay, now what is a Stirling engine? This is the diagram for Stirling engine cycle. The first step is this one, where there is an isothermal expansion. Okay, there is some say ideal gas inside this this container, where there is a piston at one end, and it is slowly increased at a constant temperature. Now in the second step, the volume is kept constant. So this volume is the same as this volume, but the temperature is decreased from some high value to a lower value. Okay. The third step is an isothermal compression. So temperature remains constant, volume is decreased. Fourth step is an isochoric increase in temperature, volume constant, temperature increases so that the entire cycle is completed. Now this is the microscopic analog of that. Instead of this container, there is a harmonic trap. Okay, and this plays the role of this container over here. The shaded area is the position distribution of the trapped particle. Now suppose I change the stiffness parameter from K0 to K0 by 2. I'm decreasing the stiffness parameter. So this trap actually becomes flatter and the distribution becomes broader. This is like your expansion process. If this is done slowly enough, then this is isothermal expansion. Okay. Now in the second step, the stiffness parameter remains same, which is the isochoric process, but the temperature decreases from TH to TC. Okay. Third step, again, this is increased stiffness parameter from K0 by 2 to K0. Okay, and in the fourth step, the stiffness parameter is kept constant and temperature is increased from TC to TH. Okay, so that is the analogy between the macroscopic engine and the microscopic model that we are going to study. Okay, let me mention here that we are going to study non-equilibrium processes. So these isothermal processes are not really isothermal. They will take place in some finite time. These are some of the results of Blickle and Bechinger. On the left-hand side, you see the work output has been plotted as a function of time of observation, okay, as well as the power generated by the engine. Now, the work output is this negative value, which becomes larger and larger as the time of observation increases, which we also expect, because if the time of observation is very large, it reaches a quasi-static limit. Okay, so in that limit, the extracted work is maximized. However, the power is not so. The power, in fact, goes to 0 at that limit, and it shows a maximum somewhere else. We'll come back to this point later. If I study the efficiency, again, as a function of time of observation, it keeps increasing and it saturates to some value. Okay, and this value is given by this expression over here, where eta c is a Carnot efficiency.
Saurabh, there is a question in the chat box. Can you see it, or I'll read it to you maybe? So Praveen asks that has these things been realized experimentally, and in particular, how do you vary temperature without changing the potential in the experiment?
It has been realized experimentally. In fact, these are the results of experiments of Blickle and Bechinger. And how we vary the temperature, there is a laser which we impinge on the particle, and that if I change the intensity of that laser, we can vary the temperature. Okay, I mean, it has no connection with this other. I mean, there is a separate laser that creates this potential, but these two don't have any connection.
I think it's okay.
Okay.
Yeah, maybe you can continue.
Okay, now we get to active systems. What are active systems? They're anything that can propel themselves. They have the property of self-propulsion. Okay, like a flock of birds here, a school of fish, or even a tiny bacteria. All of them can move by themselves, and apparently there is no intervention from external source within the duration of our experiment. Okay, so that is the definition of an active system, and it might be living. Okay, the examples that I gave, or it can be artificially prepared, like particles called genus particles. And this is a genus particle, which derives its name from the Roman god Janus, who had two faces. Similarly, the particle surface is divided into two regions, and these two have a different physical or a chemical property. For example, one may be hydrophobic, the other may be hydrophilic, or the two surfaces may react differently to the medium in which they are present. Okay. Now, if such a particle has one side hydrophobic and the other side hydrophilic, and is put into water, you can imagine that there will be a directed motion, because the hydrophobic part will be repelling the water molecules and the hydrophilic part will be attracted towards the water molecules. Well, can this system be used to enhance the efficiency? Okay, the answer is yes, but within a certain range of parameters. And here I have mentioned about the recent work which had inspired us to analyze it. This was a work by K. So's group in 2016 probably. And they concluded that an active engine has a very high efficiency compared to a passive engine. Okay, and we try to theoretically understand this effect in this work. Okay, the system is very simple. An active particle is placed in a thermal bath. This is the system.
Hi.
Yes. Yeah, hi.
So efficiency is defined in the usual way, like ratio of work done by heat input.
In the usual way, right? In the usual way.
Then efficiency will also have some distribution, right? Uh,
Oh, that's a
because
very good question, actually. The efficiency will have a distribution if I define the work by heat absorbed for each and every experiment separately. But the way we are defining here is we are calculating work done over all the experiments, calculating the average of work. Similarly, we are calculating average of heat and then taking the ratio. So it is not W by Q average, but it's rather W average divided by Q average. Okay.
okay.
Okay. There is a genus particle in some in a harmonic trap, and this is the stiffness parameter is varied cyclically. And such a particle shows some persistence in motion, which means that it tends to move in the same direction for some time. And also there is an extra noise over and above the thermal noise, which is not delta correlated. Okay. And such noise is called colored noise, and we choose the simplest form, is exponentially correlated. Okay, the simplest form other than delta correlation is the exponential correlation. Okay, these are the equations of motion that are describing our particle. Okay, this KET of x, this is the force generated by a harmonic trap. Okay, and the other thing is the thermal noise. So what we are assuming here, purely from the for analytical convenience, is that there is no activity in the expansion process. Okay, there is no activity in the external process, while in the compression process there is thermal noise, but in addition there is an activity. So the particles are such that in the expansion process it is not active, in the compression process it is active. Okay, and that can be done. For example, if you are using a live object like bacteria, Then the combustion process may have the optimal temperature in which the particle becomes active, and the hotter bath may have a slightly higher temperature, which is beyond the optical temperature of this system. Otherwise, it can be done by flashing light on the system. Okay, this is called it's a photoactivity. So activity can be induced by flashing light, and you can turn on and off this light, and you can change the activity periodically. Okay.
So the reason for not making it active during the expansion is because the efficiency gets enhanced, or is there some other motivation behind
No,
that?
it's calculation and simplicity, nothing else.
Okay.
Okay. Okay. Now this eta over here will be the exponentially correlated noise. Okay. This is the thermal noise. This is exponentially correlated noise. And to generate this noise, we use the third equation, which is called the active Ornstein-Uhlenbeck equation. If eta follows this equation, it can be shown that the time correlation becomes exponentially correlated. dH and dC are basically the noise strengths of the hotter and colder baths, and d eta is the noise strength of the activity. Okay, I hope the model is clear up to now. Okay, thermal noise is delta correlated, and active noise is exponentially correlated. Now, what about these variations? Because the spring constant is varied in a cycle, as I showed you in a diagram earlier. Now, what are the functional forms that we choose? We choose linear functional forms, linear in time. Okay, so expansion, in expansion process, if you remember, it starts from k naught, as is shown here, k naught, and at the end of the expansion process, it becomes k naught by 2. And this is the dependence, k naught into 1 minus t by tau, where tau is the duration of this cycle. Okay. In the compression process, the increase is also linear in time. Okay, k naught t by tau, and it goes from k naught by 2 to k naught. Okay, and these are the functional forms shown on the right hand side. Okay. Now let us get to the results now. So as someone raised the question, yes.
Sorry.
In the previous slide.
In the previous slide, yeah.
Yeah, so the temperature changes at exactly tau by 2, is it?
Temperature changes.
In the sense, when does it, when do you take it from hot to cold?
Yeah, it is at the time tau by 2. So these processes are instantaneous. Okay.
Okay. So
These
I
processes are
mean,
instantaneous. The step 2 and step 4 are instantaneous. Step 1 takes place for half the cycle. Step 3 takes place for another half of the cycle.
but would the system, I mean, I'm saying, I have this doubt key, would the system realize that you have reached a colder temperature? In the sense, it will take some time for it to relax to that temperature, right?
You are correct. Yeah. So if I do this,
Yeah.
then it takes some time to relax to the colder temperature. You are right. So ideally, this should have been done slowly. But anyway, I mean, much within a relaxation time, which is smaller than the time of the cycle, it will realize that it's at a colder temperature.
Okay.
Okay. So very soon it will realize that it's in contact with a colder bath.
Thank you.
Okay, and this is how the efficiency is defined. It is the extracted work divided by absorbed heat. And the absorbed heat is the difference between the work done minus and the change in energy using the first law. And work done can be calculated using Sekimoto's prescription. Okay. Now I can go directly to the results. These are some normalization, some normalizations used that are that make these variables dimensionless. Okay. Okay, these are the results. where we have shown the change in variance of the system as a function of time of observation in the first cycle only, and the work extracted in the first cycle only. Okay, the simulation results are this red line. Okay, and theoretical results are given by this blue line. Okay, and we can see that the simulation agrees very well with the theoretical results. The reason why this comparison was made was just to establish the accuracy of the simulations, because this region in which it starts from a zero variance is of no interest to us. Okay, we want to allow the engine to settle into a time periodic steady state. Okay, so I will let you know what time periodic steady state I mean. So let us see. If we allow the variance to evolve with time, and when we see that this variance has become time periodic, okay, it becomes periodic with time, then we can say that the system has settled into a time periodic steady state. Okay, we can see that even after the first period, it reaches a steady state. Okay, but just to be on the safe side, we have removed 3 initial cycles and reset the time to 0 at the beginning of the 4th cycle. Now in this region, when there is a finite distribution initially, we found that the calculation of work is analytically not tractable. Okay, it was fine for the initial cycle where the initial variance was 0, but here we need to have recourse to numerics. Okay, we need to simulate the system to arrive at the results. Okay, and this is a sort of phase diagram that I have shown. On the y-axis there is the active noise, and on the x-axis there is the noise of the hotter reservoir. Okay, and these colors represent efficiencies. Okay, we can see that the maximum efficiency is towards this corner, where the thermal noise is very small. Okay, but the active noise is very high. Okay, and we have also observed the efficiency as a function of d eta and dh separately. And this is the hunch that we had initially, and it was a pleasant surprise to find that it actually shows this kind of increase with increase in activity. So the more active the particle is, you see the efficiency keeps increasing. Okay. In the second diagram, we keep the activity constant, but we change the thermal drive. And by thermal drive, I mean the temperature difference between the two baths, hot and the cold bath. Okay, and if that is increased, there is a strange behavior, because the active particles show a decrease in its efficiency. Okay, only the passive particle, in which there was no activity, d eta was 0 for this black line, that only shows an increase in efficiency, because there is no other drive acting on it. But as soon as there are two drives, there is the active drive as well as the thermal drive. The thermal drive plays a much less significant role as compared to the active drive. If I keep dH constant and increase d eta, efficiency increases. But if I keep d eta constant and increase dH, efficiency decreases. Okay, so you see the contrast between the two drives. Okay, the one more important thing is that the efficiency reaches a saturation value at some point. Okay, if the temperature difference becomes too high, all the curves merge to some value, and this is also the case with even the Carnot engine, right? If TH becomes much larger than TC, the efficiency becomes 100%. Okay, then it becomes independent of temperature. So even in this case, it saturates to some value. Okay, not 100% of course, but it is a given value. Now we take up the question of whether a reversible engine is the most useful engine of all. we see it has the highest efficiency, as we all know, but it has zero power because the power is given by the work output divided by the time of observation. Time of observation becomes infinite when the process is quasi-static, whereas the work output is finite, so it gives zero power. Carson and Albon had showed that if instead of efficiency we maximize the power, what happens? If I maximize power, the efficiency is not given by the Carnot efficiency, but is given by the Carson-Albon efficiency. 1 minus root over Tc by Th, which is less than the Carnot efficiency, but the plus point is that it has a maximum power. Okay. But suppose I have an engine which runs at a high, which outputs a high power, and yet it has a 5% efficiency. Is that a good enough engine? Now, if it is a very low efficiency, again there is a lot of wastage in energy, right? So both the things should be taken care of. It should have a reasonable amount of efficiency as well as a reasonable amount of power. Okay, and that is quantified by this quantity, which is called the efficient power. Okay, is a product of efficiency and power. And if you see, if one of them becomes very small, the entire thing becomes very small. Okay, so if we
Saurabh,
can,
can I interrupt?
yeah,
Just in the previous slide,
yeah,
sorry.
this
Yeah,
slide.
in the first graph, what happens if you increase the activity a lot more? I mean, did you increase it? I mean, was it simulation problem, or why did you go higher data?
I mean, d eta equals to 10 was quite high. So we didn't think of going to high eta, but my guess is that it will keep increasing. But d eta
But
equals to 10 is
you
much higher than dh that we have used.
Yeah, but I had this like, have you compared it with Carnot efficiency?
So the problem with the Stirling engine is that it will never reach the Carnot efficiency.
But since your data, as you increase data, the efficiency is increasing, then I mean, it seems like it will go up above Carnot efficiency because um,
Yeah, that is a very good question, I should say. If I keep increasing data, at some point it should reach the Carnot efficiency. Yeah, we haven't tried that.
okay. Thank
Yeah,
you.
good question. So I was saying that if I can maximize efficient power instead of
I can
efficiency.
can I
Yeah,
interrupt you 1 second?
sure,
Like in the
sure, sure.
previous graph,
Yeah.
like here the efficiency increases if the particle becomes more passive.
Particle becomes more passive. Which one are you talking about?
No, dh. Okay, d eta equal to 0 is passive, no?
Yeah.
Okay, fine. I got confused with dh actually.
Okay. So if so, the more reasonable thing to do is to optimize this quantity, efficient power, instead of either efficiency or the power. And this is what we have done here. And now you see there is a stark contrast between the behavior of the engines, behavior of these quantifiers. Okay. On the left hand side, we have shown the earlier plot. Okay, this was the efficiency, and it showed a maximum efficiency in this corner. Whereas in the case of efficient power, the maximum efficient power is in the right hand portion of this curve. And here you see dh plays a much more significant role. Okay, because it keeps increasing if I increase dh, but it plays I mean, it is the contribution from d eta is much less compared to dh when we consider efficient power. Okay. Now we'll move to a simple application of this engine. Okay, often we find that an engine is connected to a flywheel, and the power generated by the engine is used to run this flywheel. Okay,
So
now this, yeah,
can
tell me.
you say about the previous slide again? My connection was lost.
if DH is large, I'm saying here the maximum efficiency is for a smaller value of DH, right, in this corner. Small DH but high activity. Okay. Now here you see efficient power is more or less independent of activity, right? So the variation along the y direction is much less compared to the
Okay.
variation in the x direction, right?
Okay.
Right. So here the thermal drive plays a much more significant role than activity. Okay, this role played by the thermal drive was masked when we were looking only at the efficiency.
So just to clarify, in the first plot you have efficiency only. In the second plot you have EP. EP is efficient power. What was the term? EP.
Efficient power is efficiency multiplied by power.
So yeah, you're comparing efficiency and efficient power, is it?
Yeah, this is efficiency. This is efficient power.
Okay. Okay. Thank you.
Okay. Okay, this is the simplest one-dimensional analog of a flywheel that we could conceive of. Okay. This is the flywheel is basically another Brownian particle, but it is not active. It's a passive Brownian particle within another trap. So this trap kind of pins this particle to within some boundaries, and this trap is also not changing with time. Okay, this is a constant stiffness constant. This left thing is our active engine, where the red particle is an active particle, and the stiffness parameter is varied cyclically with time. Okay, and these two particles are connected by a spring which acts as a shaft between the engine and the flywheel. Okay, only this spring constant is dependent on time, others are fixed. Okay, let us see what this gives. Now these are a set of coupled oscillator equations which you must be knowing. So let me not get into the mathematical details. Let us see what are the outputs. This is the variance of the flywheel as a function of time. Remember, this is not the variance of the engine but of the flywheel. Okay, we see when the flywheel is connected to a passive engine. Okay, when the left hand engine was passive, we get this black curve. Okay, but when it is connected to an active engine, we get this red curve. Okay, and whenever there is a compression step in which the engine becomes active, the red curve lies above the black curve. So what this basically means is that when the engine is active, the particle travels further from its main position. So which means it's gaining more energy from this engine. Right? So this is one application of the active engine that we have studied. So active engine connected to a flywheel generates a flywheel which moves further than a active particle connected to a passive engine. Okay, then I will summarize. We have seen that such engines may find uses in medicine and healthcare, and we consider an active particle which is trapped in some potential, and we cyclically vary this potential to generate the active engine. Efficiency increases with activity strength. Okay, but if I optimize the efficient power, this happens at high values of temperature difference. Okay, and a simple model was explored in which a flywheel was connected to this engine. Okay, and we checked that when the engine is active, the flywheel undergoes further motion. And there are some which I wish to work on, and I would really look forward to suggestions in this. Stochastic heat engines that uses multiple active particles. Now this is interesting because multiple active particles may give rise to coordinated motion. Okay, and so it can be very different from a single active particle. And then stochastic particles in higher stochastic heat engines in higher dimensions, which we are pursuing right now. And also the quantum counterpart will be very interesting. Okay, and with that, I would like to thank you for your attention.
Thank you, Saurabh. Maybe we have time for questions now.
Saurabh, can you explain how you got this efficient power plot?
Um, so the power was work divided by the time of observation,
Yeah.
and the efficiency was the way we found efficiency for in this case. Okay, and then we multiplied the two, and we got the efficient power.
But the power depends on the time scale of the cycle, right? So which time scale did you choose? I mean, you chose the optimal time scale which maximizes the power, is it?
Uh, no, actually, what the time scale was fixed beforehand, and we chose it to be 1 second. But this variation in power and efficiency as a function of the net time of observation, we have not checked. Okay, we have just varied the noises here, and the time of observation was kept fixed.
Okay.
But you are right. If I change the time of observation too, then I should obtain some higher power somewhere, and then it will depend on those parameters also. And maybe it is worthwhile to look into that problem.
Okay. And is it a popular quantity to look at? I mean, efficient power. I mean, can you suggest something?
It is not a popular quantity, but it's the more practical quantity. And here I have given the reference of a paper which probably uses it for the first time, as far as I know. Okay.
Okay, thanks.
And this is practical in the sense that neither a maximum, so an engine that has very high efficiency and very low power is as useless as an engine that has very high power and very low efficiency.
Yeah.
Hi, Sourabh. I had two sort of related questions.
Okay.
One is a sort of practical question. I mean, see, these engines, like one thing that I don't understand is when you calculate efficiency and all. Okay, so finally, of course, if you have an engine, you want to get something out of it, right? I mean,
Yeah.
You want to put in some heat and maybe get some work done.
Yeah.
But in this kind of engines, it seems like, I mean, like a lot of the things that the energy that you actually spend to run this engine, for example, keeping the laser on and then keeping this bacteria living and so on,
Yeah.
you don't even count them, right? I mean, so you're actually spending a lot of energy to just run this engine.
Yeah, that is correct. Actually, we are theoretically just probing the feasibility of this model to act as an engine, and whether the efficiency increases within if you consider this particular thing as our system. But in the but ultimately it will be practically useful if you can make it autonomous.
Yeah,
Okay,
so that was
so
my other question. So, like,
yeah.
most practical engines are autonomous. So,
Yeah.
are there like, implementations where it's kind of runs on its own?
There is an implementation in which I mean some metallic ribbons were used in connection to a cantilever, and I mean it was a kind of autonomous, but it was not a very small engine. That the dimension was of the order of 30 centimeters or so. And autonomous, one way to make it the temperature difference autonomous is to use some reactions in which the densities change. Okay, and such reactions do exist. Okay, they change the density of the medium, and that is equivalent to change in temperature. Okay, but the cyclical variation of the trap, I'm not sure how to make that quantity autonomous.
Okay. Okay.
Hi, Saurabh. I have one question.
Yeah.
So in your calculation of the efficiency,
Yeah.
Do you include the thermal noise that comes from the active part? I mean, in the definition of the heat dissipated, do you also include the heat dissipated that is towards the thermal noise, towards the active noise? Or you only include the heat dissipation to the bath that the particle is floating?
In this case, we have included the energy, the work done by the active force. That's what you are concerned with, right?
No, I'm concerned about when you define the heat dissipated in the first, towards the earlier beginning part, when you use the definition of Sekimoto.
Yeah.
So at the very beginning, when you were defining the heat dissipation for
this one.
Yeah.
Yeah.
No, even early, I don't see it immediately. It's coming very slowly. Yes, here.
Yeah.
So here you had only one thermal noise, which is this zeta.
Right.
And you considered the heat dissipated to this noise bath. Okay.
Yeah.
But now when you take your system, you have another presence of noise which comes from the noise of the activity, the active on-stem.
Yeah, that is one source of confusion in this field, whether the active noise should be a part of the work that we are considering, whether it should be a
I'm
part of
sorry,
heat.
I'm not considering about the work. I'm considering about, so work definition I can understand, but I'm talking about when you define the heat. So heat.
Yeah, so what I am saying, if I multiply both sides by dx in this manner, there will be an additional term that that will involve eta multiplied by ds, where eta is the active noise, right? And whether we include it in heat or whether we include it in work, that is not very clear. Now,
why
what
is it
we have
not
done
clear?
here,
So, because if you have a system, you have two sources of heat. And if you are asking whether how much the system, which is a particle, dissipates heat, you should consider the heat dissipation towards both baths, no?
if the particle is moving under some active force, now the work done, I mean the force, that force multiplied by displacement, whether that is heat or work. So what is your suggestion? What is your take on that?
My guess would be that you have to include the heat dissipated towards both the active bath as well as the bath that the particle is. Otherwise, you are not counting the efficiency in a right way, right? Otherwise, you are only counting the efficiency with respect to heat dissipated towards only the thermal bath that which the particle.
No. See,
no?
The heat dissipated is automatically included in this part, the way we are calculating. Because you see, we have the difference in internal energy and we have the work done, and we are not using this formula for heat. We're using the first law for calculating heat. Okay, so W minus delta E is interpreted as heat. Okay, so if I have the extra term on this side, that automatically will give me W minus delta E. Okay, because the extra part must come inside delta E, right? See, when I am calculating the efficiency, this is the formula that I'm using. I'm not using the Sekimoto's prescription for calculating absorbed heat. Rather, I'm using W minus delta E. Okay, so that extra part is automatically included in absorbed heat.
Okay.
Okay, but suppose I have an external protocol that generates this noise. For example, the particle is inherently not active, but there is some external electric field that and particle is charged and it generates this kind of active noise. And if I say that this field is also a part of my protocol, then of course we need to include that in work.
I mean, I would have to see the formula again, but I believe your answer. Okay, thank you.
Thank you.
I was just thinking that when you generalize it to the quantum case, there will be an interplay between 0-point fluctuations and thermal fluctuations. So that may also add to some other interesting effects.
Yeah, this part actually I am not very conversant with, but I vaguely think that we should use a quantum master equation in this case. I mean, can you I mean, can you just repeat the question that you were asking?
I was basically saying that when you do a quantum formulation,
Yeah.
there are 0 point fluctuations and thermal fluctuations, both are there. So there will be an interplay between these two effects.
Yeah, I guess that should be there. Yeah.
So I suppose it will have some effect on the efficiency behavior of the efficiency also.
Yeah, that should be a difference from the classical counterpart.
I had one question, like, this efficiency and efficient power, all this depend on the cycle you are taking, and for this active thing. And does it, how does it actually depend on the, I mean, the explicit type of noise you choose? Does it depend much, or?
How does it depend on explicit noise? You mean what kind of?
I mean the yes. What is the
If I
distribution
use
of
different
the
correlations,
active noise? Yeah, active
if I
noise.
use different correlations, that also we haven't looked into. We have only looked at the Ornstein-Uhlenbeck noise.
Okay.
And the objective was to show that the efficiency increases if I take the colored noise, and yeah, efficiency is above that of a simple thermal noise. Okay, but if in some special form of this correlation, the efficiency shows some other behavior or not, that we don't know. But the objective is that this engine is more useful than the normal passive engine.
So, but if you take some, like, there are other these active particles like RTP, ABP. So if you take those, do you expect these to remain the same, right? I mean,
I'm
qualitatively.
using currently pursuing a run and tumble engine, and it seems to show a degradation of efficiency. And this I don't actually understand this why they should show a degradation of efficiency, but but we are finding different behavior with a run and tumble particle.
Are there any more questions?
I think it's because like effective noise for RTP and this AOUP are different, no? RTP has one additional term compared to this thing AOUP.
Which additional term?
Like there for AOUP it will just be e to the power minus gamma T1 minus T2 kind of thing. The noise correlation at different times. But if you look at RTP, then there will be some terms in addition to this term. Whereas for AOUP only this term will be present.
No, I think for RTP it's still exponential. For ABP you get some other additional.
Yeah, it's the other way. For RTP it will just be exponential, but for AOUP the effective noise will have an additional term.
I mean, I need to think more about this. As of now, I'm not very sure why they should show a very different behavior.
Are there any more questions? Okay. If not, let's thank Sourabh again for the nice talk.